Welcome to NPTEL. Myself Dr. Jayanto Das from Department of Metallurgical and Materials Engineering, IIT Kharagpur. I will be teaching you advanced materials and process. So, today we will start a new topic of on advanced material, which is shape memory alloys. The shape memory alloys, the term itself says that the material remember its shape. So, there is a large group of shape memory materials. So, here the materials means it could be alloys, and such kind of transformation has been also observed in some polymer or ceramic system also. However, these alloys and the shape memory behavior are very much well linked and are useful for many different types of engineering applications. And therefore, it is of our interest to discuss these advanced materials. The shape memory behavior in a alloy can be achieved due to some phase transition, which is controlled by temperature and stress. And since phase transformation is involved in this process, therefore, we must recapitulate the phase transformation, this particular subject, in different metals and alloys, and we should try to learn and try to think about how they are linked with this shape memory behavior. So, today we will try to focus more on the phase transformation in metals and alloys. The phase transformation usually classified into two major categories. The first one is called as continuous transformation, and the second one is the discrete transformation. The continuous transformation here means that the system that become unstable with a very small composition fluctuation, like higher order phase transition. The example, if I tell you, you will understand it more like a spinodal decomposition. You must have heard the spinodal decomposition in your undergraduate days. However, we will again discuss the same, and some part was also discussed in some other topics. So, in case of a spinodal decomposition, we have a solid solution which has a average composition of x 0. Okay. And if we make a very little composition fluctuation, a composition fluctuation means if we have to deplete a area, then definitely there will be enrichment, because the atom will move to the nearby site. Okay. And in such a case, there will be a localized fluctuation in the system, okay. Localized fluctuation in the composition in the system, and that always decreases the free energy of the system, means system always go in favor of making the composition fluctuation. It also says in other way that there is no activation energy for such kind of process, because for making any nuclei of a second phase particle, or let us say if I have a parent phase, okay, and I want to introduce a product phase into it, then there will be a activation energy barrier, okay, which is controlled by the surface area, the volume, and so on. But in this case, where a very small composition fluctuation always make the system stable, because there is a net decrease of the free energy of the system. And so, this spinodal decomposition is a type of continuous transformation. So, in this particular diagram, you can see that x 0 is the average composition of a solid solution, and there are solute atom and which can segregate in some localized region like here and here. So, let us say a B type of atom in A. Okay. So, that basically segregated somewhere, and there is always a net decrease of the free energy by changing a small composition fluctuation, and finally, which will try to make a higher and higher fluctuation, and it always stabilizes the system. Now, in case of a discrete transformation, which is often like a first order transformation, and a first order transformation is characterized by a discontinuity in the enthalpy curve and so on. So, you have seen those things in the earlier lectures. So, here when there is a parent to a product, there is a sharp interface, okay, in between parent and product phase. So, to form a product, we have to go through a nucleation and growth type of process. If a nuclei has to form in a matrix, if a nuclei has to form, then there is a need of a interface, and this is like a first order transformation. The usual example of such discrete transformation are like solidification. Here we already know that if we take a liquid and the solid nuclei has to appear, first a particular cluster will appear, okay, and those are if they have a greater size than the critical size of a nuclei, then they will be stabilized, and there should be a need decrease of the system, and we need some activation barrier for such a case. Also, a Martensitic transformation is also a first order transformation. Here the transformation goes through a nucleation of the Martensite plate and its growth in the austenite phase. So, this is a discrete transformation. So, as an example here schematically I have shown that I have a alpha matrix, and here is a beta phase which is the product phase, and there is a interface. Okay. There is a sharp interface between them. So, this is the two major types of phase transformation. However, we can also think a phase transformation by several other aspects. What I want to mean that we can think about the order of the transformation. Okay. So, here we can classify a phase transformation in terms of whether they are first order transformation or there is a second order. Second order means that it occurred not there is no discontinuity in the curve. So, like a glass transition I talked about, which is a second order transformation. Okay. So, in the enthalpy versus temperature plot, you will not get a sharp discontinuity. Also, since when a product has to form, the atomic rearrangements has to be made. Here the atom can rearrange themselves by a simple shear, okay, and make the product phase from a parent matrix or parent lattice, or the atoms can go for like a civilian motion. A civilian motion in a street, you can see that each and every person is going into different directions. Okay. So, this is like a civilian, whereas if you think about a movement of the military, where there is a group of people who are making equal footing to a particular direction. Okay. So, there is basically no relative movement between the two person or two soldier. So, that is like a military type of transformation. Okay. So, a military type of transformation does not need a diffusion. So, these are called as a diffusionless transformation, whereas in case of a solidification we need diffusion of atom and partitioning between the atoms are required in case of a solidification, or let us say in a steel, if there is a eutectoid transformation and so on, then the diffusion of atoms are required. Okay. So, this phase transformation we can also classify in terms of whether the atomic movement are diffusional or diffusionless, whether there is any relative movement between the atoms or not. However, whenever there is a discrete transformation, as I said, it goes through a nucleation and growth process, then this nucleation could be also two different type, where a nucleation could be occurred homogeneously all over the places in the parent phase. Okay. So, like a containerless solidification. Okay. So, in a containerless solidification, the nuclei will appear all over the liquid in different places and then they will grow and fill up. Okay. In that particular case, we may get a more homogeneous microstructure, but if we chill or if we cast a cast iron or let us say aluminum alloys in a cast iron block mold, then we will see that three different layers are appeared, because the solidification has initiated from the chilled layer. So, there the cooling rate is faster and heterogeneously the nucleation and also act as a heterogeneous site for nucleation, and therefore, the nucleation start from the surface and it require less activation energy, where homogeneous nucleation require higher activation energy, because you have to create a surface and creation of surface require excess energy. However, in case of heterogeneous nucleation, the surface is already there, only some atom has to move and it need less of that activation energy. So, that is more favored. So, if you like to solidify a liquid in a mold, then heterogeneous nucleation will start at the interface between the mold wall as well as in the liquid. So, that is the case. However, this growth could be also interface controlled or let us say something like a diffusion controlled growth. So, let us say a product phase, if it has to grow in a parent matrix, then diffusion of atom may be required. So, that growth is mostly controlled at that moment, it is a diffusion, and if like a Martensitic type of transformation where there is no long range diffusion is required, then only the interface moves. Okay. Interface moves means and it completely covered the whole parent phase, it become a interface control, and there are many other examples of such cases. So, we can also classify or we will try to think or we will try to identify a phase transformation process in these particular aspects. Now, let us come to a diffusional phase transformation. A diffusional phase transformation simplified that long range atomic diffusion is required to initiate this phase transformation and to complete the phase transformation. Okay. One is the initiation, which is somewhat like nucleation and also the growth. So, mostly there are so far 5 different types of diffusional phase transformation has been observed. So, these 5 types are polymorphic transformation. Here you can take a pure metal. A pure metal, the first example is like a iron. Okay. Pure iron, I am talking about pure iron. In case of pure iron, if we go above 910 degrees centigrade, then we will get actually gamma iron. Okay. Gamma iron is the pure iron which has a crystal structure of face centered cubic, FCC. And now, if we cool it down, then the gamma iron will transform into alpha iron, and this require nucleation of alpha iron in the gamma iron boundaries, because this is a solid transformation, and here the growth of those gamma iron nuclei will occur, a alpha iron nuclei will occur during cooling of gamma iron. So, this is a polymorphic transformation, where there is no compositional changes. Okay. Now, in case of a second type of diffusional phase transformation, which is called as a precipitation process. So, in a precipitation also it is also controlled by nucleation and growth of the precipitate. Like as an example, I show you here one aluminum copper type of phase diagram. Okay. So, this is just a schematic diagram, and here A and B, these are two different component of the system elements, and they have a eutectic type of phase diagram, and they have a very low slope of this solvus line. This is a solvus curve, and here we can simply choose such a composition and heat it up. This is the temperature axis, okay, and go up to here. Then we will get a single phase alpha. Okay. And now, if we quench it, okay, if we quench it, then we can get a supersaturated solid solution, or we can have a slow process where this beta phase will evolve here, okay, and as we cool down, this precipitation of beta will occur in a alpha matrix. What I want to mean that during cooling, so let us assume that this is the microstructure of alpha, which is kept at this temperature, okay, and so beta will nucleate here, nucleation of beta will occur, and then they will grow. So, this is a precipitation phenomena, because from one solid we are getting another solid which is precipitating from the parent matrix. So, this is also a precipitation phenomena, and there are very similar phenomena observed in a edge hardenable aluminum copper system. The third type of diffusional phase transformation is the eutectoid transformation. In a eutectoid transformation, it is a solid transformation, means this is in a solid phase which is solid 1, where we will get basically two different solid. So, S2 and S3 from S1. So, here it is a gamma to alpha and beta. This is just a schematic we have shown, and a specific example of such transformation is the gamma austenite that transform into alpha ferrite to and cementite. Cementite is a metastable phase also, and eutectoid transformation we all know. So, here let us say alpha and beta will evolve from gamma. Okay. Now, there are also other two different type of diffusional phase transformation that occur, like ordering. Okay. In ordering, there is not very long range, however, diffusion is required, but not like solidification. Okay. So, here beta to beta dash transformation, another example in copper zinc system. So, here you see, if we choose a composition near to 50-50 of copper and zinc, okay, copper zinc type system is shown here. So, here from beta we will get a ordered phase which is beta dash. So, this dash actually represent that it is a ordered structure. So, so a specific type of atoms, means let us say the zinc atoms occupy some specific site in a FCC or some other kind of structures. So, this is called as a ordered transformation. However, the last type of transformation, that is called a massive transformation. So, the massive transformation here, the important feature of such transformation, that it is a composition invariant transition. Okay. So, like there is no compositional change. Okay. Here you may think that since there is no compositional change, then there is no need of a diffusional transformation. It is not like that. Okay. So, here one example of such massive transformation is shown here. So, if we have such kind of peritectic type of transformation, where from beta we will get actually alpha. However, please notice and take a note that there is no Martensitic like transformation involved in this process. Okay. This is a complete diffusional phase transition from beta to alpha. Okay. So, this is called as a massive transformation which involve diffusional movement of the atoms. Now, let us come to a diffusionless or military, or another way we call it also a displacive transformation. Okay. So, in this particular case a structural change occurred due to a coordinated movement like military movement of the atoms or group of atoms, okay, and relative to its nearest neighbors. So, there is almost the relative movement is almost 0. So, this diffusionless transformation or displacive transformation could be many different types, and we will try to focus on these two type of transformation. One is Martensitic transformation, another one is QuasiMartensitic transformation. You may not have heard this QuasiMartensitic earlier. However, this QuasiMartensitic is a type of lattice distorsive displacement. So, this particularly mean that there is a distortion in the lattice. Okay. So, distortion in the lattice somehow means that in this particular case the kinetics and the morphology of the product phase is not dominated by the strain energy. This is a very classic example which was reported by Dale et al. Quite long time ago in 1982, and he told that a FCC to FCT type of structure that evolve in manganese X system. So, here X stands for copper, nickel, iron, or let us say gold. So, this is a QuasiMartensitic transformation that occurred from a FCC phase to a FCT type of structure. So, here a paramagnetic phase which shows some sort of antiferromagnetic type of behavior. In that particular case, so here this is the temperature versus composition axis, and you can see these are the substructure that is involved in this product phase. Here product phase is the face centered tetragonal, and this is the parent phase is the face centered cubic. If we think about that how a FCC phase transform into face centered tetragonal, then we simply take a FCC lattice and stretch it into one direction, okay, maybe in the z axis, okay, or along the c axis. Then you will see that it is very easy to show how a FCT structure can evolve in a FCC lattice. So, there is a limit of that composition beyond which that particular QuasiMartensitic transformation does not appear, and so these are mostly twin involved in this process. Okay. But you may also tell me, sir, in case of Martensitic transformation there is also twin is involved. Unfortunately, all Martensite does not involve twinning. Okay. So, this is something new we will learn today. So, let us continue with the Martensitic type of transformation. In case of Martensitic transformation, here be very specific that kinetics and morphology of the product phase are not dominated by the strain energy, which is like a QuasiMartensitic. So, in case of QuasiMartensitic it is not dominated, where it is dominated by the strain energy. So, it means that strain energy must be higher in case of Martensitic transformation. So, we will slowly discuss what are they. So, an example is like a FCC phase that transform into body centered tetragonal in case of a steel. It is an iron carbon system, very common example that you all know. Okay. And I show you here one of the microstructure of such martensite. So, here this is a martensitic plate, and this is let us say a parent austenite, and this is a body centered tetragonal in a FCC. So, these are all martensitic plate. So, this martensitic plate so far we have seen in the textbook that these could be lathe type or plate type. However, there are also two other type of martensite morphology people have observed. So, in total there are 4 different type of morphology observed. One is lathe type, another one is the butterfly type, one is could be the lenticular type, and another could be thin plate type. So, this morphology is very important, and it also depends on how these structures evolve. So, let us try to summarize what is quasi-martensitic transformation and what are the typical signature of such quasi-martensitic transformation. So, 3 common aspects of such quasi-martensitic transformation has been reported by Dale et al. So, there should be a lattice distortion, and this lattice distortion is very small and deviatory dominant, and the change in the lattice distortion is continuous or nearly continuous. The second is that it may internally there could be twinned microstructure. So, here twin structure is the substructure in the product phase that gradually build up during cooling below the critical temperature. Here since it is a magnetic and so on, so we have seen, and a mechanical lattice softening which occur by the elastic shear constant when it is approaching to T c. Okay. However, because of the small lattice distortion is involved, so the ratio of the strain energy to the driving energy transformation is very small, and that is the reason actually since this lattice distortion small. So, the morphology is not dominated by that particular case. Whereas, in case of a martensitic transformation, there are some typical signatures. What we looked at here, the displaciveness, okay, or the displacive transformation or the lattice distorsive type. In that case, we see a shear dominant shape change of the lattice. So, there is a definite shape change involved in the lattice, and diffusion is not required at all. Okay. Whereas, there could be a sufficiently high shear strain energy in the process, which has also been reported by Cohen et al. From very long time 1982. So, the definition of martensitic transformation is therefore is not based on the identity of the transformation product. So, if you looked at a product phase and if you find twin, then you will automatically say, so this is a martensite. It is not like that, but rather how the new product has formed in the microstructure, in the parent microstructure, and that is the characteristic of a martensitic transformation. Initially you may think things are not very clear, but as we progress you will see that we will understand what a really martensitic transformation means. And there are many different tools which has been discovered till today, which characterizes a typical martensitic transformation and how are the typical signatures. A martensitic transformation is also often characterized by some sort of transformation hysteresis. So, there are 4 critical temperatures that characterizes a martensitic transformation. So, if we start with a martensite from room temperature, or maybe we can start from a austenite from a higher temperature. So, these austenite could be cooled and then martensite will appear here. So, this is the onset of the transformation, which can be estimated through the tangents, and then the transformation continues, and then here is the end of the transformation. So, here all the phases here are the martensite, and here martensite plus austenite, and here it is the austenite. However, if we start with the martensite heating, then it needs some extra energy to transform. So, here we call it as a austenite start. This suffix S stands for start and F stands for finish. So, here is also S stands for start and finish. So, here we have basically martensite plus austenite, and here the all the martensite transform into austenite. Okay. So, almost at the peak temperature we can imagine or assume that 50% of the transformation from Martensite to austenite has completed, or otherwise here. Very similar feature people have observed in case of a dialectometer. Okay. In dialectometer, here the length changes or dimensional changes are measured. So, if you take a small rod of such a Martensite, then the very similar way you will see such kind of hysteresis, where here is the austenite start and here is the austenite finish, and here is the Martensite start, because the slope changes, right. So, here is the there is a plot which is linear and then the slope changes. So, the transformation has begin here. Here is also the slope changes, that is why the transformation begin here. So, here this is actually MF, okay. And the Martensite finish and austenite start, there is always some sort of lag, you can see actually. However, these temperatures are somewhat a bit closer, okay, because transformation require some extra energy and so on. So, in case of resistivity measurement, very similar thing has been observed, some similar hysteresis we are talking about has been observed. So, in this particular case, we have noticed that the temperature and the resistance axis, in case of a iron nickel system, the transformation begin here, which is the austenite start, and here is the austenite finish, and here is the Martensite start and here is the Martensite finish. Okay. So, you can see there are several systems which are not at all still. Okay. So, copper, aluminum, manganese, nickel, here is also with chromium, here is iron nickel system and is the gold cadmium system. So, Martensitic transformation occur in many different systems, and those all systems shows some hysteresis, whereas somewhere the hysteresis could be small or hysteresis could be larger. So, these are a differential scanning calorimeter plot or dialectometer, or let us say resistivity measurement that shows such kind of feature. However, the morphology of the Martensite could be also little different, and in this particular slide I show you that in case of a iron nickel carbon system, if we change carbon content and the transformation temperature if changes, the Martensitic start temperature begin here, then we will get these 4 different morphology which I discussed with you just a few minutes ago, with a lathe, butterfly, lenticular or thin plate. And these different morphology is involved with different kind of substructure. So, a substructure means actually that like a tangled or let us say dislocation or dislocation and twin. So, not only twin can be involved in this process. So, in a lathe we see only dislocation, whereas in case of thin plate twin is only involved. Now, if we think about schematically that this is a austenite and this is the product Martensite, then this is the plane which is the interface between austenite and Martensite, which remain unrotated and undistorted, is called as the habit plane. So, the habit plane could be different in case of lathe, butterfly, lenticular or let us say thin plate. So, this is the direction of the habit plane actually, okay. Or this Martensite could be with a substructure of twin or dislocation. Okay. So, there are many different substructure appear, and the strain energy can change the morphology of the Martensite from a lathe to lenticular to thin plate and so on. So, higher the temperature and the lower the temperature that has involved with these 4 type of transformation. Okay. So, you can see the orientation relationship or Ks relationship, or let us say the Nishianum type of relationship, or let us say Grenier-Torrento type of relationship. There are many different relationships has been evolved, and we can characterize this Martensitic transformation with the product and so on. So, in next class we will continue with this discussion to understand the phase transformation and how they are interlinked with the shape memory effect. Thank you.